Hi, my name is Samantha Jagosinovis, and I will be doing my presentation. So I'll start by going over case at connection 1, which I'm doing it over the first question. I'll go ahead and read over an overview of what case 1 is. So pyruvate kinase PK catalyzes rate-limiting ATP generating step of glycolysis, in which PEP is converted to pyruvate. Multiple isoenzymes of pyruvate kinase exist in mammals. Type L, which is found in the liver and kidneys. Type R, which is expressed in erythrocytes. And type M1, which is found in tissues such as muscle and brain. And type M2, which is presented in self-renewing cells such as embryonic and adult stem cells. So how is pyruvate regulated in the cell? Well, one of the main ways that pyruvate is regulated is allosterically by intracellular signaling pathways and metabolites. Per Israelson's article, this means that PKM2 integrates signaling and metabolic inputs to modulate glucose metabolism according to the needs of the cell. So pretty much this means that PKM2 can serve as an inhibitor, activation site, or both. So the regulation by end product inhibition and regulation by interconversion of active and inactive forms. Each PKM2, PKL, and PKR subunits contains one binding site that is specific for FBP and distinct from the active site. So this means that FBP is notorious for serving as a binding act to increase PEP binding, promote tetramerization, and stabilize the enzyme tetramer in the active state. PKM1 does not bind FBP due to structural differences at the FBP binding pocket. However, PKM1 isoform naturally exists as the stable tetramer that has high constitutive activity, rendering it insensitive to most of the allosteric effectors that act on PKM2, PKR, and PKL. PKM1 and PKM2, once it's activated by FBP, have almost identical kinetic parameters, and they're both locked into the same type of three-dimensional conformation. The only difference is that the protein that's encoded by isoform-specific exons, so the binding site FBP and dimer-dimer interface. Other very well-studied regulators also include amino acids and glycolytic metabolites, which allow coordination of PKM. This allows the coordination of PKM activity with metabolic fluxes and other pathways. However, these effects usually require very high concentrations, and most of the time they don't have a very high visible effect. So mainly this is because PKM2 is usually regulated allosterically by numerous small molecules and metabolites. This also does question the importance for the physiological regulation of PKM2. Hormonally regulated pyruvate can be by insulin and epinephrine, which have been suggested to modify the regulatory influence that adipose tissue may have on pyruvate dehydrogenase, but this isn't as common. So back to our normal or regular question. Many types of cancer cells are predominantly glycolytic and overexpress the oncoprotein MYC. Interestingly, the classical oncoprotein MYC has been found to promote preferential expression of pyruvate kinase type M2 over pyruvate kinase type M1. So per Harper's textbook, in Chapter 17, glycolysis proceeds at a high rate, forming large amounts of pyruvate, which is reduced to lactate and exported, producing an acidic local environment in the tumor. Glycogenesis in the liver uses lactate for the energy expensive process, and is responsible for much of the hypermetabolism seen in cancer cachexia. So what other pathways may cancer cells be diverting substrate to? The PKM2 is usually found in cancer patients, per the Warburger effect and mTOR. Per the Warburger effect, mTOR was termed to be a key activator. Also per Sent et al., demonstrated that PKM2 was a crucial glycolytic enzyme in the oncogenic mTOR-induced Warburg effect, in which hypoxia-induced factor 1A and CMYC HNRNP cascades are the transducers of mTOR regulation of PKM. Insulin also upregulates PKM2 through phosphatidylsatide 3 kinase, mTOR-mediated HIF1A induction. But all in all, ROS is the reason for the reduction of PKM2 activity. So a bit of an overview of tumor cell metabolism. This is in reference to the article specifically to tumor cell metabolism. So the cancer cells use glucose at higher rates compared to non-cancerous cells. Smaller fraction for oxidative phosphorylation does enable cancer cells to incorporate a greater fraction of glucose metabolites in macromolecule synthesis instead of expending it on CO2 production. This means that anabolic metabolism shunts glucose-carbon from glycolysis biosynthetic pathways like the pentose phosphate pathway PPP. The PPP produces ribose biphosphate and PRPP, which is required for nucleotide biosynthesis. PPP, in its oxidative form, also generates NADPH, which does support the proliferation of cells. This is why PKM2 also helps in the proliferation process and is the main reason why PKM2 is found in cancer cells. PKM2 is also responsible for the final step of glycolysis, and it's key in this process. The preferential expression and allosteric enzymatic activity of PKM2 provides the cancer cells with a growth advantage in vivo without the accumulation of ROS. Moving on to case 4. This is going to be more of a case study on a patient and figuring out what their diagnosis is. An overview of the case is a previously healthy 2-month-old female presents with jittery spells several hours after breastfeeding. Her mother reports she has not given the baby anything to eat other than breast milk since birth. The baby has only recently been sleeping for more than 2 hours between feedings, and that's when the mother reports these symptoms started. Laboratory results are consistent with hypoglycemia, but are otherwise unremarkable. Epinephrine is administered and there's no increase in blood glucose, but there is an increase in blood lactate. So this was a very important section to kind of guess what the actual disease was. It also mentions that her physical exam revealed a liver edge 4 centimeters below the right costal margin, and pretty much confirmed that it was hepatomegaly, which is enlarged liver. Blood glucose levels also increase after breastfeeding, but she can't maintain blood glucose levels within normal range while she's fasting. So I did a process of elimination on this one. I went over the diseases that were given and listed off the symptoms to see if any of them matched with what this patient was presenting. So hereditary fructose intolerance, the symptoms for that are nausea, gas, chronic fatigue, and malabsorption, which the patient had none of. Galactosemia, which the symptoms were loss of appetite and vomiting. If the patient was breastfeeding, she did not have a loss of appetite and there was no mention of vomiting, so I did cross that one out. Glycogen storage deficiency in large organs. That was one of the bigger indicators that it could be this one. But she also had hypoglycemia and high levels of lactate, all of which match the symptoms of this patient. Basically, what glycogen storage deficiency is, though, is that I cannot mobilize glycogen. I didn't want to just stop there. I also wanted to keep checking all the answers to make sure that this was the correct one. Glucose 6-phosphate dehydrogenase deficiency. So the symptoms for this are anemia, fatigue, dark urine, and jaundice, and pain in the abdomen and back. There was no signs of anemia or fatigue. There wasn't any dark urine, no mention of jaundice and or pain anywhere. So the answer was glycogen storage deficiency. Here are my references that I used for both case connections. Thank you for your time.